Hey class, Mr. Newman here, and welcome to what is this next week here of our environmental science class. As I mentioned in the course introductory for the week, there's going to be probably some disruptions, so just going to go ahead and record some of the lessons so that way we have time for more of the in-class labs and things of that nature this week versus just spending all the time going through the textbook. So let's get jumping on this. Some of this is going to seem like some review because we talked a little bit about this in week number one, but as we have state testing coming up in October, it's important that we stay up to speed and fresh on a lot of these things because they're going to do that assessment test based upon 8 weeks of school. So they're going to do the totality of units one and two. So this week we're going to go through all of chapter two. Next week, all of chapter three. And then so chapters one, two, and three make up unit one. So then we'll move on to unit two, and hopefully all that goes smoothly. So let's just jump right in. And this section one talks a little bit more in depth about the scientific method. So I'm going to talk about how to organize and analyze data, draw conclusions, repeat experiments, communicating results, these things that, again, we've talked a little bit about, but we're going to go into more depth. So I have this picture here of these scientists who have knocked this wolf out, and they are measuring it. Now, it's tranquilized, they measure it, and then they tag it, they send it back out. And they do this is because this is a way of collecting data, tracking migration patterns, and tracking growth patterns, tracking all kinds of different things, pretty much trying to understand the day in the life of a wolf for a myriad of reasons. So when you come to this one, why might they be measuring the tail? Because the tail is a symbol of growth on a wolf, and that's how they use that information. So quickly, our objectives for this section one are to list again and explain the experimental method, the scientific method, as we would say, why a hypothesis is simply not a guess, describe two essential parts of a good experiment, understanding that not all experiments are good. We talked a little bit about that before. Describing how scientists study subjects in which experiments are impossible. Some things we're curious about, but we just can't really run an experiment, and to explain the importance of curiosity and the imagination in science. And that's probably going to be one of the big ones we need to understand is right here is that to understand the curiosity and the imagination. So we'll focus a little bit more in depth on that as we go along. So the experimental method, scientists, again, science is the study of. The scientists make the most of their discoveries in using the experimental method. That's important to say they use the most of their discoveries. A true scientist, that means that their discovery may be completely counterintuitive, completely contradictory to what they thought or what their hypothesis was. However, regardless of the outcome or what they even wanted the outcome to be, that they use the most of that, and the information doesn't become what they call redacted or curtailed based upon the discoverer's presuppositions. So that's just something just to keep in mind. We have to understand that the method consists of asking a series of steps scientists worldwide use to identify and to answer questions. And the biggest part of this is observing. Observe, observe, observe. Science is all about listening, watching, using the senses, just really being aware of what's happening in the world, and then asking the big question, why does that happen? When does that happen? And does it have to happen? Or could it be changed how it happens? Could it be more efficient? There's a million things that can get discovered through the observation process that are questions. And we talked a little bit about Science talks about examining the physical world and asking ourselves all of those questions and examining everything. So, again, observation is the process by obtaining information by using the senses as well as the information. So, for example, it's one thing to smell, but it's another thing to smell something and then to do something with it. By just same thing as visual acuities and things of that nature. So, and this again is the first step of the scientific method, and it can take descriptions, drawings, photographing, and its measurements. So those are the big things. So sometimes observations can just be broad in general just by noticing, and other times observations are going to be specific by, again, measuring and getting more into detail. We talked about metrics and why those are important. And we're going to go back into that as well. So, understanding a hypothesis. A hypothesis is a theory or explanation that can be tested. So if it can't be tested, it can't be a hypothesis, then it's just a guess. Or a hypothesis also has to do with it's based on observation. So a hypothesis, I remember if you remember back from second, third, fourth grade, it was called an educated guess was the key terminology. An educated guess, meaning it was brought on by these observations and not just some kind of thing that we arbitrarily pull out of our brain. And this is the second step of the scientific method. And again, it is merely not a guess. So it should make logical sense and it should follow from what you already know about the situation. So a hypothesis, that's a key thing there, is that it comes from what you already know about the situation. Predictions are statements made in advance that we kind of say this is what we think is going to happen, and if the hypothesis is correct, this is what we think is going to do. It's going to line up with that, and so the prediction is used to test a hypothesis. The prediction is formative in the experimental process. So hypothesis is predicting. It's important to understand that any hypothesis, as we remember, cannot be that it can be disproved. And every time a hypothesis is disproved, the number of possible explanations is reduced. So it's deductive. So it's important to understand that. Remember, you can't prove a hypothesis indefinitely true. You can only fail to prove it false. So that's important to remember because that keeps the scientific method going and keeps the questions coming. So we can zero in on the best explanation. And so experimenting, that is the procedure under which carried out, understanding that we have to know that we have the keys here are controlled conditions, demonstrate or test a fact, theory, or general truth. And an experiment is performed when questions arise from observations that cannot be answered uh, with additional information and observations. So that pretty much means we have to do some testing. We got to do some finding out. That's not just readily observable the answer. So we're going to have to investigate. Think of it as an experiment as an investigation. So an experiment should be designed to pinpoint cause and effect relationships. Very important to understand that. So good experiments are going to have two characteristics. A single variable is tested and a control is used. The variable is the factor that changes in an experiment in order to test a hypothesis. And to test one variable, scientists usually study two groups or situations at one time, with the variable being the only difference between the groups. For example, you see this a lot in medical testing. They want to test the effectiveness of a new drug. They'll have a group of people come in all suffering from the same condition. One will be given the potential new medicine that's going to hit the market. One group will be given what's called a placebo or a sugar pill, if you will. They both think they don't know who's getting what, but they're both ingesting what they think could be medicine, and so the only variable is what they're ingesting. And so then the those who collect the data will determine whether or not does the group who takes the real medicine, do they experience benefits, or do the group who take placebo, do they experience benefits? Because sometimes results can be what are we called psychosomatic, meaning mind over matter kind of thing. You see that sometimes with people. So this is one of the reasons why a lot of times the subjects of an experiment are not told which group they're in, because that causes some issues there. So important to understand that. And so the experimental group is that group in the experiment that is identical, and then the control group is the group that serves as the standard. So in that instance, the group that got the placebo would be the control group, and then the experimental group would be the group who got the new potential drug that might hit the market. So and then they got to analyze the data. So the data is the pieces of information. So for example, using that analogy of the patients and the people with the new potential drug, they're going to start asking those folks who did get the new potential drug, how do you feel? Have you had any side effects? They're going to start collecting all those data and those evaluations and those what this is called feedback. So in that kind of a study, feedback can come from actually speaking to the patient, maybe taking blood tests, maybe other types of tests that would measure, like for example, if it was a cancer drug, maybe they would do scans and see if the sizes of tumors reduced. If it was some kind of like a plant study, they would maybe look at the control group or the experimental group and measure new sprout growth, things of that nature. So that's the now where we start to organize and analyze data, and then they put that into graphs or different things to where it can be compared. So, data is only as good as you can organize it to show people and to understand it yourself. For example, if I had all these random numbers and all these different feedbacks and I just kind of threw them into a bucket and pulled them out, that doesn't help anything. But I got to organize that clearly and concisely so that anyone can take a look at that and say, oh, well, this is maybe what's going on. Because some people are really good at doing experiments, some people are better at analyzing data. So a good scientist makes that data usable for other people, so maybe somebody else who's better can analyze that data at a little more depth. So these are just some examples of some different charts and tables that might be the result of experimentation. And so we'll drill down more into that. But then we got to draw some conclusions. So scientists determine the results by their experiment by analyzing their data and comparing the outcome of their experiment with their prediction. So, for example, if I thought I had in my experiment of this new drug that this new drug was going to reduce cancer cell growth, okay, I'm going to compare that to if I do scans on these individuals, did their cancer growth reduce? Did the amount of cancer cells reduce? That's going to start to tell me, did my prediction stand? Did my hypothesis, uh, was my hypothesis disproved or not? So ideally, the comparison will give me an obvious conclusion. Sometimes it doesn't. That's just the nature of some experiments. Sometimes when you do an experiment, you discover holes in your thinking, and you realize, no, okay, I'm going to have to redo the whole experiment and tighten up. For example, maybe I discovered that in this group of people who were in for a new experimental cancer drug, well, maybe now I realize that there's actually another variable between men and women. So now I need to do the whole thing over again, only using one gender. So I can maybe say, okay, is there some kind of uh, particular instance in which this drug is more effective by gender? So those are things uh, that in a perfect world that would not reveal itself, but if it did, we would be willing to go out and to redo the experiment and to come to more better conclusions. So drawing conclusions, again, often the conclusion is not obvious. Sometimes we have to use mathematical tools, percentages, ratios, things of that nature. Those are what we call statistics. We'll get into that. And then here's the other thing. You also have to be willing to and able to repeat your experiment. For example, if you do an experiment and it says, hey, I found the secret to life. If that can't be duplicated, it's not valuable science, that's what we call, if you'll remember, we talked about pseudoscience. So the experiment has to be replicable. So that is absolutely key and critical. So we do that. We look for supporting evidence. We'll talk more about peer review. That's what's called communicating the results. For example, if I feel I found this great answer, I'm going to put that out to peers. They're going to test that, and then that's a great thing because then that now my experiment will hold more water in the community, and if it's been deemed good and sound science, that takes it further into helping humanity. So we scientific articles include the question the scientists explored, and this is important because again, think about it: two heads are better than one. Should always, 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 if you're in science, be willing, well, ready, and really happy to have your results examined by your peers, and it shouldn't be something of scrutiny. It should be something of honor. So then we got to look at the correlation method. Um, Correlation method is important. It's when we talk about when we use the experiment to answer questions is impossible or unethical. So, meaning, for example, it wouldn't be ethical for me to test the lifespan of a person with both kidneys removed. That would not be something that would be ethical. We don't want to do that. So then we're going to try to maybe use the correlation method. And so we can maybe look at instances that have a linear dependence variable, meaning, for example, can we track the lifespan of people who we know are in kidney failure or something of that nature? But there are just some experiments that we might be curious about that are just unethical to carry out, so we use correlation. So here's a good one. An example is the relative width of a ring on a tree trunk. It's a good indicator, the amount of rainfall in a given year. Now, trees produce wide rings and many rears in the dry years, but here's the thing: we don't want to go cut down a bunch of trees to find out if that is true. We might actually, say, hey, we need to just find a different way to do that. Maybe when a tree dies and it's cut down, then it's examined. So scientists conclude that settlers may have been the victims of unfortunate timing. Here you go. We look at the drought patterns and we can look at these things, and we use data to look at correlation. So this is important, and without data you wouldn't have this information. So um, it's important to understand that that they don't necessarily prove cause and effect, but they also do say, hey, there's something more to look at here. There's some more correlation that we need to look at. All right, so now we get into the scientific habits of mind. So these are important things. Again, can't stress it enough that the first habit of mind is curiosity. If you're not curious, that's if you really stop and think, all science has come from curiosity. Skepticism is another one. Skepticism, sometimes we look at that in a negative connotation in our world today, but skepticism is also a form of curiosity. It's that thing that says, who validates that, and who says that that information is accurate. All right, so don't forget, skepticism is an extremely important part of that mindset. And again, it's okay to ask questions. It's okay to, again, question everything. This means that good scientists don't believe everything that they're told. That's key. And let me go ahead and stress to you, too, that this also means that you don't believe everything that you even read. I know today we're told read books, which is a great thing. We should definitely read, but also remember that it's always good to get a sampling or a myriad of opinions, and then make observations and then start to test that which we feel should be tested through our skepticism. So, again, the third habit is you got to be openness to ideas. If you've ever met somebody who's closed minded, and this does happen in the science world, they just think something and they're not going to be convinced otherwise. Uh, that is also counterintuitive to the scientific process. It's really counterintuitive to the general development and openness of humanity. So progress comes from the idea of saying, hey, What if we're wrong? Again, we talked, if you'll remember, in week one, we talked about there was a time in which people thought the world was flat. And if we look at the ventures of those across the ocean, that was, in a way, just a gigantic scientific experiment to say, what, if anything, is out there? Because those people, back in those days, they thought and were told there was a good likelihood that they were just going to fall off the edge of the earth. But they said, you know what? We don't think so. We think there's more out there, and we're going to go out there and find out. So, um, lastly, they use the term intellectual honesty. We could also talk about integrity. We talked a little bit about ethics, if you remember. If you are in the scientific community, you have a duty-based ethical mindset to be honest about your discoveries, honest about your experiments, honest about the questions you ask. Even the frame of an experience has to be framed around a high level of ethical and moral standard. So, we should always ask: is the experiment that we're doing, is it meant to help and to further humanity, or is it meant to hinder humanity? And so these are good questions, and this plays a big part of the scientific community. And we got to share imagination, creativity, but we also have to be able to conceive new ideas. And to be honest, we have to be able to say, "Hey, listen, I like what another person said or thought. I'm going to elaborate upon that, or build upon that, or do more with it." And so, again, there's no. I heard the expression one time years ago. It said there was no such thing as a completely new idea, just ones that people build upon. So, and this is how we explain and to when he did that, we should know that it was something that was very formative, and we're going to go more through and talk about that. So, last thing here, you guys will see in your assignments for your vocab words for this section one. Here they are, and if you will go through, I have them all done one by one. So when you're doing your vocab assignment, don't reinvent the wheel. Just come back to this video